So, okay, hi guys, I'm live. I want to do, it's time for math lesson and so forth, numbers and, just do a lesson. Let me get this so I can see it. All right, there you go. I got everything here. Hi guys, how you doing? My hair is drying, so I'll need to comb it more than usual for a little bit. We're doing some math stuff. Let me think if I get this all clear in my head what I'm going to do. Okay, it might be musical too along the way. Okay, first I want to talk about the way that the formulas for area, surface area, and volume are calculated in geometry, and how I use calculus to get quick formulas for such. Okay, first of all, we have a circle. If you have, this is going to work. And now, what do you see about the circle? The circumference divided by diameter equals, that's supposed to be a C, pi, and that's supposed to be a D, and that defines pi, and then and that is so the circumference equals pi times d, but d equals 2r, so c equals 2 pi r. That's the circumference of a circle. Now, watch as I use this mental imagery plus calculus to define what the area of a circle would be, using calculus as well. Now, here's the center. You have the circumference here. Now, in calculus, when you integrate, you take sums, infinite sums of things. So I'm going to add a little circle that's a little less smaller in diameter. Then I'm going to add another circle a little less smaller, and I'll keep adding little circles until I get an infinite number of them, but finally go down to the point where the radius would be 0. And the sum of all these circumferences will make an area of the circle. You can see that just logically. So what I'm going to do is to get the area. Let me use my eraser here. Yeah, I thought of this on my own, but then again, doesn't mean I'm the only one that ever thought of it, and blah blah blah. Okay, so to get the area of the circle, I want to integrate the circumference to pi r from 0 to r, or it could be from 0 to r. Oh wait, the way I explained it was I went from r to 0, but from 0 to r is just as good, plus it implies upward motion, which is good in this situation. How do you integrate this from 0 to r? To integrate a monomial, you take integrate 3x squared, you take the exponent here, add 1 to it, and divide the whole thing by that. So the integral of that would be 3 halves x cubed. That's just the property of, it's a formula in calculus, how you do a integrate a monomial. So what I'm going to do here, if I integrate this, I take r to the next higher up power, which is r squared, divide by the 2, you get the 2 divided by 2 is 1, so you get pi r squared. So the area of the circle equals pi r squared. I showed that intuitively and using calculus rather than some long, hard thing. So where do I go from there? The area is pi r squared based on calculus and a little imagery. But now we do something else. That's the area of a circle. Now I'm going to talk about a sphere. What's the surface area, that's SA, of a sphere of radius r? Well, it turns out that that's 4 pi r squared. So it take the surface area of a sphere can handle 4 areas of circle of equal radius. So it means if I took a circle the size of a baseball and made enough of those to cover a baseball surface area wise, I would get 4 of these. 4 times the area of the circle equals the surface area of the sphere of equal radius. That's just a formula. I don't know where they came up with it, but somehow we believe it. So now I'm going to do the same thing with calculus. I have a circle, actually a sphere this time. The surface area of the sphere could be out here. Then I'm going to take a little less surface area, a little less surface area, and all these surface this is in 3 dimensions, even though I can't draw it such. All these surface areas are going to add to the volume of the sphere. They're going to fill it in. So what's the volume of a sphere? It's going to be the integral of 4 pi r squared. That's from 0 to r. I'm writing terribly. That's how you get the surface area, the volume of a sphere. And now what's that going to be? So let's erase here. Let's erase and do it. Sorry, this is a long lesson. The surface area. Oh, the volume of the sphere. Okay, so the volume of the sphere equals integral from 0 to r of 4 pi r squared. It's an integral of all the surface areas that are added from 0 to r to make the volume of the sphere. So what is that? Well, let's use our integration. If you raise this power by 1, you get r3, r cubed. Divide by that, you get 4 thirds and pi. So there I just showed that the volume of the sphere is 4 thirds pi r cubed. And that's a formula you can find in almost any math book that covers the topic at hand. And is that section of math. So there you go. I derived the volumes of a sphere and the surface area, and the volume of a sphere and the area of a circle much more intuitively than you will get in a standard math book, I think. I'm not going to rip you out and say, I guarantee no one thought of that. Oh yeah, right, there's that guarantee, right? LOL, Rick. Anyway, what's the next one? I want to do one, that was that. I want to do one on Euler's theorem. So I have E to I theta equals cosine theta plus I sine theta. It's called Euler's theorem. Or Euler's formula, sorry. This formula. I'm not going to go on about this too much right now. That's the basis of system engineering, essentially. And I just want to make an observation. Exponential functions can be expressed in terms of trigonometric functions. Sine and cosine are trigonometric functions, and exponentials are considered not trigonometric functions, but complex exponentials, or exponentials to a complex power. In this case, it's imaginary, but that's still complex because the report just happens to be 0. Is expressible in terms of trigonometric functions, which isn't obvious as we're looking at it. But I want to do one little trick with this before I go. That couldn't be all I talk about, right? Why would I bring it up just for that? If I have cosine theta plus I sine theta, what's the radius of the circle that it makes on the complex plane? This is x. This is I y. How do you know the radius is 1? How do I know that? Well, the x value is cosine theta. The y value is I sine theta. Or if you think of it absolutely, sine theta is this distance, and cosine theta is this distance. So the question is, how do I know? How do I know what? What am I saying here? Oh, I know what I did wrong. Oh, okay. Well, actually, I know what I did wrong. This is a circle of radius 1, right? Now, if cosine theta equals maybe here, and sine theta is maybe here, let's make it, let me think. Oh, I get it. You go like this. This is cosine theta, this is sine theta. Yeah, that's how it works, Jimmy. You go x, and then you go y, and then the result is the r, the radius of the circle implied. So how do we know that's 1 right here? Let's blow up the circle. Let's blow up that circle a little, that triangle a little more, and see how we can find that out. Okay, so my circle was this, and I had this, and that's not a very good line. I had this, and I went X, Y, and then what's the radius? Well, to do this, let's call this A, B, and C. That good? Yeah, okay, let's do that. So if A equals cosine theta and B equals sine theta, then how do I know C, the radius? Let's call it R. That's dumb. C is dumb. R. How do I know that R is 1? Well, it's a very simple trick. There's a trigonometric formula that says sine squared theta plus cosine squared theta equals 1. It's a trigonometric formula. And according to Pythagorean theorem, a squared plus b squared equals r squared. And since a is cosine theta, you have cosine squared theta plus sine squared theta equals, well, lo and behold, sine squared theta plus cosine squared theta according to trigonometry is equal to 1. Therefore, 1 is the radius of the circle on the complex plane. Always called, in this case, since R is 1, it's called the unit circle because it means it's a circle with radius 1. So there's a little trick for you guys to know what you're doing as far as the complex, the complex plane and other formula, not theorem, formula. I like to do things in threes all the time. We do another thing. That was 2 things. Let's do another thing. This is in music, but it's mathematical. Let's talk about intervals and the ratios. So an octave is 2 to 1. Fifth is 3 to 2. Fourth is 4 to 3. Interesting, because when you make the first overtone, you go up to twice the frequency that gives you an octave. You go up another fifth. You go up you go up 3 times the original pitch. Oh, and this interval is 3 divided by 2, and it happens to be a fifth, and then you go up another one from 3 to 4, and 4 gives you a double octave or octave. 3 gives you an octave plus a fifth or fifth. The difference is a fourth, which is 4 to 3. So let's start with those simple ratios. I mean, who says they're simple, but they're ratios. Octave is 2 over 1, fifth is 3 over 2, and fourth is 4 over 3. That's background. Now, what would I like to talk about this? Okay, let me think here. In equal temperament, you have 2 to the, in our Western in the 12th tone equal temperament chromatic scale, you have 2 to the 1/12th power. 2 to the 1/12th power is a semitone, half step. Okay? Power over root, 12th root, because if you take 2 to the 1/12th power and multiply it by 12, that would give you how many? That would give you 12 of these, what I'm calling a half step. You get back to 2 to the 12 over 12, which is 2 to the 1, which is 2. So 12 half steps of each half step being 2 to the 1/12th power make an octave, which means the octave is divided into 12 equal steps, like we all know. At least it's true, and something a lot of people know. Okay. Oh, I got that. But you could set up the system up different ways if you really wanted to. What if I divided the fifth into 7 semitones, just for the heck of it, just to show the math is possible to do that? A fifth is 3 over 2. If I made it 7 semitones, it'd be, per fifth, it'd be 3 to second, 3 halves to the 1/7th power. That'd be that'd be a perfect fifth divided equally into 7 parts. Really weird, but you could do it. Okay, and basically having an octave divided into 13 half steps would just be 2 to the 1/13th power. This ratio would be the ratio of a semitone if there were 13 semitones per octave instead of 12 like there are. So that's interesting, I guess. A little more work on this, though. Let's do a little more study on this. let's add intervals. What's a fifth plus major third? Triangle up means major. Well, that would, intuitively, that's a major seventh. Let's figure that out mathematically. A fifth is 3 over 2. Okay? A third, major third, is 3 4 is actually 5 fourths. Okay? And that just is, you can check it out. And then 6 fifths, which I'll call it like this, 6 fifths is a minor third. So let's see what that ratio is. Well, this is for major seventh. So major seventh is this ratio multiplied out. So 4 times 2 is 8. 3 times... Again, I'm getting somebody calling me. 3 times 5 is 15. Let's do this over here. 4 times 2 is 8. 3 times 5 is 15. So get 8 over 15. I mean, 15 over 8. 15 over 8 is a major seventh. See that? So how do we see that? Somebody's calling me. If a major seventh is 15 over 8, then you could say, since a double octave, oh actually no, 2, 4, 8, 16. Oh yeah, 2, 4, 8, 16. 2, 4, 8, 16. I think if I say an octave, dang, my phone just hit an end. Okay, my phone just did a dive there. If an octave is 2, double octave is 4, triple octave is 8, quadruple octave is 16, I have that 16 over 16 over the 16 is 4 octaves. So 15 over 8 is a major seventh, and therefore I could say a half step is 16 over 15 would be a half step. At least one way of looking at a half step would be 16 over... The phone keeps dropping. That's not good for the... Oh, gosh. Phone... the vibrations of the person calling me is making my phone drop. So 16 over 15 would be a half step. Because a major seventh is a half step less than the octave. And that extra half step would be 16 over 15, such that a major seventh plus a half step is 15 over 8 times 16 over 15. And since the 15s cancel, you get 16 over 8, and that's 2. So a major seventh plus a half step is an octave, because an octave is 2 over 1. So there's that little fun. Let's do one more example. Yeah, right. Keep calling somebody. Whoever's calling, I mean, is what I'm trying to say. I'll stood the book up. That should help. And necessity is the mother of invention. I just stood the phone up. I just stood the book that was on up, so it won't knock down again, I don't think. How about the ratios for a major sixth? Major sixth. What's a major sixth? A major sixth is a perfect fourth. Fourth plus a major third. Okay? Alright, in fact I'll just write major 3 because that's what I've been doing. That's a major sixth. What's a perfect fourth? Perfect fourth is 4 over 3. Major third is 5 over 4. So major 6 is this times this, which is the 4's cancel. The 4 here and the 4 there cancel. That makes 5 thirds. So major 6 is 5 thirds. Then how do I go to an octave from there? Well, major 6. Let's start over. Yeah. A major 6 is 5/3. But we know that a major 6 plus a minor third, I'm going to call that upside down 3. Minor third, that's a minor third, is an octave. Let's see if the math supports that. A major 6 is 5/3. A minor third is actually a minor third is 4, 5, 6/5. Just works out that way. So what is an octave? Well, the 5's cancel. You get 6/3. 6/3 equals 2, and the octave is twice, so it makes an octave. So major 6 plus a minor third is an octave. You can play with the intervals that way with the numbers. Leviticus, peace, love, and rock and roll. Okay, now I go.